Okay, so as many of you are aware, I studied in a cardiopulmonary lab at the University of Oregon for my PhD program. And so this is getting into the stuff that I really like. So I'm super excited that we're talking about the cardiovascular section. Usually this is in week 7. But for reasons mostly that because we have like a pseudo spring break during week 7, I didn't want to do any of the fun stuff, or what I consider to be the fun stuff, to be done online. So we're going to start off talking about the cardiovascular system, and the first few days are going to be kind of review, and then we're going to get into how the cardiovascular system works during acute exercise, and then later on in the semester we'll talk about some changes or training adaptations. So for this video, we're going to talk about neural control of the heart and a little bit about cardiac output. So when it comes to control of the heart rate, there's what we call intrinsic control and there's extrinsic control. So intrinsic control is control that comes from the heart itself. And we see this in pacemaker cells, as we've talked about in human physiology. These cells can generate action potentials on their own. They don't need any input from the brain. They will be able to create these action potentials. Now, that's not to say they won't listen to the brain or listen to these signals. They absolutely will. But if for some reason they don't get a signal from the brain, they'll still have action potentials. Now, the SA node is the primary pacemaker cell in the heart, and you can see it's right here up in the right atria. On its own, if you got rid of both the sympathetic and parasympathetic activity or tone, it would fire around 100 times a minute. And the job of the SA node is to transmit the signal onto the AV node, and it also tells the atria to contract. Then we've got the AV node, and the AV node is kind of down here on the bottom of the right atria, and it does two things. One, it kind of holds on to it holds on to the signal from the SA node for just a split second. This allows the atria to contract fully before the ventricles contract. After that delay, it will send the signal along so that ultimately the ventricles contract. It does this by sending the signal to the bundle of His. Okay, notice that we're right in here. Okay, and then from there we go to the Purkinje fibers that send the signal down, and then the signal wraps back around and up the ventricle. Okay, and with these pacemaker cells and the way that the cardiac cells are designed, the atria contract as a one unit and the ventricles contract as one unit. Now we have extrinsic control, and so this is control coming from without or outside of the heart. Okay, and this is where the autonomic nervous system comes and plays a role. So parasympathetic is primarily dominant during rest. Heart rate can be as low as 20 beats per minute. I've measured my heart when I had what's called a vasovagal response. It's when I saw the guy from Louisville a few years ago break his leg and have a compound fracture in a NCAA tournament game against Duke. I don't react real well to that, and my parasympathetic nervous system really kicked in, and my heart rate was around 25 or 26 by my math, so could have been completely off. But like I said, if we don't have the parasympathetic tone, heart rate might be as high as 100. Parasympathetic nervous system is dominant when we have low heart rates. Sympathetic, on the other hand, does the opposite. It increases heart rate. It's the primary system that's affecting the heart rate when we get up into that moderate intensity exercise, so heart rate's above 100. And in some cases, in a healthy human, heart rate can be as high as 250. Now, I want to make clear that it's not one or the other. You've just got different levels, and so it's kind of like fats and carbs, right? We talked about the crossover effect. Well, it's something similar with the sympathetic and parasympathetic nervous systems. When the parasympathetic tone or activity is high, generally sympathetic activity is low, and vice versa. And so it's more of a sliding scale as opposed to on and off. Now, hormones also play a role, and this is how the sympathetic and parasympathetic systems get their signals across. So the sympathetic releases epinephrine and norepinephrine. These will increase heart rate and stroke volume, and ultimately we're going to increase the duration of this sympathetic response. Remember, epi comes primarily from the adrenal gland, so it's dumped into the bloodstream, and this goes everywhere, and it just takes a while to clear out. On the parasympathetic side, you could look at acetylcholine, which will slow things down. Now, I want to finish here by talking about diastole and systole. Remember, when you hear the word diastole, think relaxation. So we've got that here, relaxation. Okay. Now, with diastole, we want to know how much blood's in the heart at the end of diastole, or at the end of relaxation. And oftentimes we call this preload, or when we talk about preload, we're referring to the pressure that's in the heart before contraction, okay? And that's because of the blood. The more blood, the more pressure. Filling time is how much time the heart has to fill up. So when heart rate's low, there's plenty of time to fill up. But as heart rate increases, there's less filling time. And that could be an issue, but we'll get into that later. And then we've got stroke volume, which is just how much blood leaves the heart per ejection or per contraction. And then on the other side, we've got systole, so we've got end-systolic volume, so how much blood's in the heart at the end of contraction. Ejection fraction is the percentage of the blood that leaves the heart during contraction, and remember, it's close to 50 or 60%. We don't really lose, or we don't really eject all of our blood. And then this also corresponds with afterload, or all these kind of are related. So afterload is the pressure that the heart is contracting against, which is aortic pressure. If aortic pressure exceeds ventricular pressure, then then this valve right here, the aortic semilunar valve, remains closed, and then blood doesn't leave the heart. The more pressure there is in the aorta, the greater the more your heart has to work. Okay, we don't want our heart to work hard; we want it to work efficient. And so that's where we're going to end for this video, with the introduction / review of cardiovascular system.